In step 7 of this Institute of Practical Learning course on self-awareness, we explore more deeply the physical world, what we call wobbly, which is basically analog, and how we can use mathematical modeling to help us get more of an insight as to the kind of data and the level of detail needed for our minds to understand what's going on.
So 128, let's start with 128. When people were looking at how to interpret this wobbly world and digitize it with digital computers, they decided, I'll tell you a little story. In 1967, which probably seems like 1,000 years ago to you, I was recruited by a company called Boeing from the UK to go to America and work on helicopters. That's why I used the word helicopter before. Now, what's crazy about this is the helicopters I was invited to go over there and learn and do some work on was actually called the CH-47, which is commonly known as the Chinook. It's a helicopter that looks a bit like that. Blades there, blades there. There you go. That is a really awful drawing of the Chinook helicopter, and because I am a little bit of a perfectionist, I'm pretty sure the rear rotor is above that one. It's a while ago, 50 years ago, I think, or thereabouts. I think that's how it is. So they said, Graeme, we want you to come over to America, help us build a model of this particular helicopter, because we've got a bit of a problem at the moment. We can't get it to lift enough. We want it to be able to lift stuff from space out of the water. So I thought, well, that's nice. They offered me a lot of money at that time. So science, I was talking to you before about scientific computers. Now, by then, IBM had just moved on from what was called the 7000 series of computers up to the 360 series. Before that, they'd had the 14. You don't need all this detail. Basically, it was to do with computers, and I got involved when I was a young man in computing. Now, right from the get-go, I was very interested in the relationship between the way the human mind thinks and how computers work. Because I was a mathematical modeler of the physical world. So humans live in the physical world. If you're going to build a mathematical model of a helicopter that's flying along, and talk about wobbly, they're really wobbly, in the physical world, with humans on board, I might add, you've got to be able to think about the relationship between the physics of the world, the air, the speed it's flying at, its weight, the angles of the blades and everything like that. And you've got to be able to translate those somehow into you've got to be able to digitize it and create a computer model. So I went over this. This IBM 360 was the fastest computer in the world at that time. And it had the information that it worked on was basically stored in here. This is the memory of the computer. And there were places, it was nearly all to do with numbers, to be honest. It was equations and numbers. Now, the numbers, again, I am getting into a bit of detail here, but I'll tell you the relevance of it is to the way the human mind tackles living in this shifting variable world. And trying to build a mathematical model of a computer, of a Chinook, is kind of pretty close or getting closer to what humans have to do, let's say when they drive a car or work something out that's of a mechanical nature. So the memory of the computer, it has things called bits. So the numbers, as I say, were integer and floating point. So integer numbers, because they're limited in the number, you can work with them at the same time as you can work with characters. And not just characters, but symbols. For example, multiply, divide, that kind of stuff. So each of these things like this was broken up into bits and bytes. Now you're going to think, oh my God, I'm going to stop watching right now because this is mega boring and electron computing. It isn't. I'm trying to avoid that. If you think about it, what I'm going towards is, how does your mind hold information? Is it held in bits? Is it held in bytes? And especially, it really doesn't matter how many. So what you'll find when you work with memory and bits and bytes and stuff like that is this number becomes important. Now, I'm not going to go into the details of it, but this number is part of what's called binary arithmetic. So bits, bytes, and what you actually found, you and I mostly are used to talking, when we think of numbers, we think it goes from 1 to 10, or from 0 to 10. So we write a number down like this. Why should I be talking to you about this? And the reason is, the human mind doesn't necessarily work in chunks of 0 to 9. How many, when you see things, when you save data into your mind, you select a certain amount of data and you put it away in your memory. And it isn't digital, it's not from 0 to 9 and 10. And it's not hexadecimal. I can tell you, cracking a dump from an IBM 360, reading hexadecimal isn't the easiest thing in the world. It doesn't really come naturally. But the people who developed it were mimicking in some ways what actually does go on in the human mind, which by computer standards is highly complex. But you do it, and you do it automatically, and your brain is wired, and all the paths in your brain are wired to do super complicated calculations. That's a skill that's within you already. You don't really need to know this. Here's the point. I'm telling you this stuff because I have an agenda to talk about this, but it isn't really important for you to know the value of pi. The world we live in, the physical world, is phenomenally complicated. But as I say, we do it automatically using, broadly speaking, analog. We use analog types of computing, not digital. So in that respect, we are not like computers. We use analog processing. But when I first got to Boeing to build this model, they showed me the best analog computer they'd got. And they showed me this digital computer, this IBM 360. And they said, Graham, these are the kind of equations, and they were long, complicated equations that describe the motion of this. They said, can you program them in the analog computer, or can you program them in the digital computer? And to be honest, the digital computing was much, much easier because the analog computing was limited. Whereas digital computing really has utterly taken over from analog computing. Here we go, I had to do it in digital computing. But remember, this whole thing is wobbly. There's one rotor and there's another. They're all sitting on this helicopter, which is flying along, and it's wobbling. And it's a nightmare, really, to try and program it. but I had to go. So I used to go back to the scientists with the result of my calculations, and it didn't represent the actual what was happening to the helicopter. And they said, Graham, it's not accurate enough. We need it to be much more accurate. I said, well, how accurate do you need it to be? And they said, well, when these blades go up and down, it's not just the first big vibration. It's a bit like going backwards and forwards in a bath. You get these what's called resonances, resonant sounds. And when you think back to the physical world we live in, if you hit a piece of tin or something and you hear a sound, it resonates like that. But then if you play a violin, that sound you hear, that's a resonance as well. And as well as the first part of that resonance, you get other minor vibrations as well, and they're called harmonics. So when you're listening to music, your ear is very sensitive to these vibrations, not just the main vibration, but the subtlety of the harmonics. So if you want to stop that helicopter crashing out of the sky or those blades falling off, you need to understand not just the first big resonance, like woo, like that, but you need to know that some of these harmonics can have quite a big effect. Now, to do that, you need more accurate calculations. And they wanted 10 decimal places. Well, I thought, cranky. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 dp. Anyway, digits, so I'll go for digital places. Anyway, so 10 decimal places. Now that meant I needed to think about how capable was this computer, this IBM 360, of doing calculations to 10 decimal places? Or was it necessary to have approximations? Now, if you're modeling a helicopter, there's a limit to how approximately you can make your calculation. But if you're a human being living in the physical world, if you want to be able to function effectively, you have to make approximations and you have to filter out, and the information you collect has to be filtered and narrowed down so that it's useful to your purpose of living as a human being. And the reason I'm talking about these computers is to show you the huge difference between what a computer has to do and what you have to do as a human being. Because you do have bits and bytes, as it were, in your memory, but it's not clear how big they are. You do have to do calculations with numbers and with characters. You do have to read and stuff like that. And also, you have to be able to run and walk and talk and do all those other things. And they all involve your mind doing calculations. So let's move on from this stuff.
These first 8 or 9 steps in this IPL course on self-awareness are to raise your own awareness of what kind of entity a human being is and how totally different we are to computers. And all this talk of artificial intelligence and robots taking over and so on, it's all complete rubbish. Because once you understand what the 4 different kinds of intelligence and how important they are in the interaction between human beings and the whole society and globalization, you'll begin to realize that by developing soft skills and developing the other intelligences that are within you, other than academic intelligence, you will be able to future-proof your life and have a very successful career.